It is my pleasure to introduce William Kimball from the University of Texas at Austin. He is a graduate research assistant in chemical engineering department. Today, he will be discussing interactions, clustering, and rheology of highly concentrated antibody solutions. And without further ado, I'll go ahead and pass it over to you, William.
Thank you so much. Thank you very much for having me here today, and very excited to give this talk. So I'm going to try to go to the presenter mode. So can everybody see the slides?
Yes, I can on my end, so you are
right,
good.
Great. So yeah, so I'll just jump right in. So just a brief background or motivation is essentially we are interested in proteins mainly because they are a very popular emerging class of biologics for pharmaceutical treatments, and they are very promising, but they have a couple issues when it comes to development, and we talked about this here. So so essentially, the stability and viscosity of MABs at high concentration are an issue, and this is because you have a lot of behaviors that can happen at high concentration. And so we could see from this chart, for example, we have reversible oligomers, we have filament at another end here, and we also can have precipitation. And all of these are mediated actually by mainly short-range attractive protein-protein interactions, or PPI, in solution. And these clustering behaviors can affect the viscosity, opalescence, and even phase separation. So how can we understand these clusters and their relationship to viscosity? So first, we need this is just an intro to some of the previous literature results, is that when we do measurements at low concentration, they're not very good indicators of viscosity at high concentration. And so a lot of low concentration techniques include light scattering, although you can get S of zeros from static light scattering at high concentration. But the issue with this is I have two examples here from two different papers. One of these papers on the left shows that when you take S of zero measurements from static light scattering, which essentially give you an indicator of the clustering behavior at the large length scales in solution, so very large clusters, for example, they don't correlate very well at different concentrations. So there's not really any clear indicator at low concentration going to high concentration. And this is on the right here is a paper from our group where actually we did see a trend that when you measure S of zero, there is a trend, but it doesn't go between MABs. So if you're starting a brand new MAB and you don't know anything about it, and you get these measurements, you don't know how well the correlation is between S of zero and viscosity. So essentially, as I mentioned before, we have the main reason for clustering and forming these reversible oligomers in solution is that they are mediated by short-range attractions, or a combination of electrostatic, hydrophobic, and van der Waals forces. And we want to capture these in molecular dynamics simulations because they allow us to have that microscopic view as to what's going on at very small length scales for a couple MABs, for example, that you can't really get with light scattering. And we can see that there's a lot of different behaviors you can get. For example, here at the chart on the top, this is more what we would consider kind of clustering behavior. If you can see my cursor here. But we can also get behaviors like networks with molecular dynamics. So we can capture, it is possible to capture complex behaviors in solution. So this is a main technique that we will use to understand clustering. The one drawback with using computational methods is that we need to decide how much detail we need on an intramolecular scale. And that's because if we try to do atomic resolution modeling on antibodies, they're quite big. They're about 150 kilodaltons, so it's excessively expensive, even with very advanced computer systems today, at least. And so what our group decided to opt for is a kind of middle ground where we use a simplified coarse-grained model, so the 12 bead model, which you can see here on the right. And so what that allows us is that it has enough resolution on an intramolecular scale, since we are more interested in how clustering between different molecules behaves. So we need more intermolecular scale, high resolution there. But this is a good compromise too, because instead of using this continuum representation here, we can still capture the effects of, for example, charge patches by assigning values to different beads, which I'll go into in just a few slides here. So as I just mentioned, this is the motivation for our 12 bead model, or just a concrete example from the literature, where this is data from this paper by Yadav, and essentially what they found is that there's this MAB1 here, and it has a large negative patch in one of the CDR regions. And essentially what they found was that when you try to get viscosities while you're concentrating your protein, they go way up very quickly. So you're not really going to get close to 200 mg per mil with this MAB1. And they noticed that MAB2 in their study, which has on the same CDR region, there's a much smaller patch. And so you can see in red here that you can get to higher concentrations without increasing the viscosity too much. So what they decided to do was they engineered this new M5 to replace a few of the residues in the sequence of the CDR region to reduce the size of this charge patch. And you can see that doing so will reduce the viscosity. So we can learn from this that essentially we can target specific beads. So for example, in our 12 bead model, we can target the bead that is correlated to this CDR region, and we can adjust the values assigned to that bead in simulation to modulate different effects in molecular dynamics simulation. So here is essentially the work that we've done using this bead-specific attraction concept. And so we use this method on vedolizumab studies. And just a little bit of background on vedolizumab. It's a antibody that's used to treat Crohn's disease and ulcerative colitis. And the interesting thing about vedolizumab that we found for this work that we're discussing here is that vedolizumab can have different subclasses. IgG1 and IgG2 and IgG4 are the most common. And we took a look in the literature at specifically IgG1 and IgG4 subdomains. And essentially, we found that in the literature, the usual behavior is that the viscosity of IgG1s tend to be lower than IgG4s. And what we found was that there will be a case that I will discuss very soon, that we found a case where IgG1 is actually more viscous than IgG4. And essentially, we can modulate the subdomain effects because there's different charge distributions here by assigning different charges, or different values, I should say, in different attractions on the beads in the dotted lines here. So just to kind of tie everything together before I kind of go into some of the results, is that we wanted to confirm the results of our simulations with an experimental technique to make sure that it lines up with experiment. And normally there's not that many, for what we want to do, there's not that many techniques that can be used to directly probe concentrated protein solution to get meaningful results. For example, multiple scattering starts to become significant as you concentrate in protein with light scattering. And so what we decided to use is this small angle X-ray scattering as a complementary technique to our molecular dynamics simulation. And so with our setup, we can probe length scales from about 1 to 100 nanometers, where a single MAB is about 10 nanometers. And so this is just a very brief diagram of how you actually conduct the experiment. You put your sample, and it's very simple. You just shine an X-ray beam on the sample. Some of the beam will be scattered, and you can use a detector to measure the intensity. And what we ultimately want from this is we want this Q vector here, the scattering vector, and we want to keep track of what the intensity is at different Qs. And the reason why this is important, it comes back to this S of Q. We use this equation that's called the decoupling approximation. And it basically says that the intensity at each Q here has a corresponding component for intramolecular shape in this P of Q here. And this S of Q, the structure factor, is what we are interested in because it gives an indicator of the structuring at longer length scales. So this kind of leads to the objectives of the study, where we want to characterize protein-protein interactions and the formation of clusters. And we're going to do this with molecular dynamics simulation and use SAXS as a complementary technique to verify experimentally which simulations are correct. And we're going to be using this 12-bead coarse-grained model with bead-specific attractions, and we're going to get S of Qs from simulation. And we will use this to determine the effect of the MAB structure, the pH, ionic strength, and cosolutes on this structure factor. And we will relate the cluster formation to specific protein-protein interactions on specific beads. We want to determine the viscosity from PPI using cluster size distributions that I will explain later that come from the X-ray scattering simulations. And we also want to use this SAXS technique as a screening tool to help early stage discovery and development for proteins. So now I'm just going to kind of go into some of the details of the simulation that we used. So as I mentioned again, we're using a 12-bead model, but we are using this in LAMMPS, which is a pretty commonly used software for molecular dynamics. And how do we kind of get the scattering data? Because we can't really simulate in a simulation, right, the actual scattering experiment. So we have to get it somehow from the trajectories that we get from molecular dynamics. And so how we do this is we get I of Q curves, so the intensity, by Fourier transforming a real space density correlation function, which can be readily calculated from molecular dynamics simulation. And we will then get this structure factor by dividing a properly scaled I of Q from the correlation function, and then we'll divide by the form factor P of Q. And the P of Q is essentially I of Q in the dilute limit. So we can also get that from molecular dynamics. And what we can do from there is we can essentially define what it means to be a cluster. So typically we'll take MABs that are within a certain distance of one another, and we can then get cluster size distributions from the simulation. And this is also just some more detail about how we set up the simulation. So we use 3 potentials. The first one is just van der Waals attraction on each bead. Then we will get a screened Coulomb repulsion, and this is where one of our main parameters, Q, comes in. Q represents the charge that we put on each bead for Coulombic repulsion, and we essentially can change the ionic strength of our solution by adjusting this kappa by calculating the Debye length from the experimental ionic strength. And then the short-range attraction that I mentioned, we're only putting it on specific beads, in particular the gold beads that you can see in the model in the bottom left. And we can adjust how strong those attractions are with this K parameter. And so this just uses standard Yukawa potential for that. And essentially, we're able to modulate different subclass effects or model different CDR regions using this system. It is important to note that we actually are going to put in our simulations, we put Q on each bead, and that's it's the same charge on each bead. And even though that might not be accurate. If you, for example, take a look at residues on a specific MAB and an atomistic representation, that might not be the most accurate, but we found actually that normally the net charge on MABs is so small that actually putting different Qs on each bead doesn't actually affect the results significantly, because it ends up being that the net charge of a MAB in solution is between plus or minus 6, and so the Qs are small to begin with. So now kind of relating all of this and putting everything together, so we have these two charts. This is vedolizumab data, and so we have the dotted lines are the experiment, and we have the best SAXS fit from simulation. So we have a library of simulations essentially where we have many Q and K pairs, and so we built a library and we find the best one that will match the experimental data. And so from this, we can get, as I mentioned, we can get the cluster size information. We can get this fractal dimension, which essentially describes roughly the morphology of your clusters. And so we see that the more traditional techniques of KDs and S0 from light scattering, they show that that the IgG1 here should have a lower viscosity than IgG4 because its overall appears more repulsive than the IgG4. And this is a special case here because the IgG4 being less viscous than the IgG1 is not very common in the literature. And we see that these two light scattering results show that they don't accurately describe why this IgG1 is more viscous than the IgG4. However, we see from our best fit modeling that we have better correlation, because we would expect that if something is more viscous, the average cluster size should be larger. And we also would expect that the short range attractions should be stronger if the viscosity is higher. So these are consistent with the experimental results. But so it comes down to, why is this system more viscous than the IgG1? Why is it more viscous than the IgG4? And so we seek to answer that using the X-ray scattering data that we can get. So just very briefly, I'm going to introduce some models from previous publications. One of them is this Castellage model. And so this is a model that essentially does take into account the cluster size of proteins to predict viscosity. And it also takes into account the cluster size distribution. So like whether or not you have lots of smaller clusters or just a few larger clusters. So this model will account for that. However, there are some advantages and disadvantages to this current model. So it does predict viscosities pretty well using these cluster sizes, but the limitation here is that it assumes that there's no excluded volume. So the particles don't occupy space and the particles are allowed to overlap. That's why in this diagram, just to give you a picture, there's no excluded volume at all. Everything is just green here. And the additional limitation to this model is that it's a fitting algorithm, because this B and D parameter are fit parameters, and as it turns out, the physical significance of these fit parameters, the interpretation of them is not very clear. So we wanted to improve a viscosity model to account for excluded volume effects and the packing. And I'm not going to go into detail with this. Another student in the group did the derivation of these principles here, but I would refer you to this paper, Bossis from 1991, on some of these concepts. But essentially, we want to account for hydrodynamic stress dissipation in clusters to improve our viscosity model. And so we found this paper here that kind of goes into some details. So if we have rigid rods, we see that the stress is proportional to n cubed, so the number of particles in that rod cubed. If we have perfectly lubricated particles, which can easily slide past one another, the stress is proportional just to the number of particles in the system. And then finally, the case that they talk about, which is closest to what MABs behave like in solution, are fractal clusters. And so essentially, the stress dissipation is proportional to the longest dimension within that cluster. And you get this expression here where the stress is proportional to n to the power 3 minus df over df, where df is the fractal dimension. And as I hinted earlier, the fractal dimension is a rough indicator of the morphology of a cluster. And essentially, it accounts for the fact that clusters don't pack perfectly in space. There's always going to be voids and empty spaces if you try to pack MABs together. And so this DF can kind of characterize the degree of how much space is being inefficiently packed. So the second concept we need for our improved viscosity model is the true volume fraction. And so essentially, as we mentioned earlier, the inefficient packing of MAB clusters, it increases the viscosity. But why does it do that? It's because it increases the occluded volume, and which is defined as essentially space that is inaccessible to kind of floating MABs that are outside of a cluster. So you can see that in between the packing here, there's these yellow spaces. And the important thing to note is that even if the occluded volume is larger, much larger than one of these MABs, it still is closed off, so they won't be able to kind of diffuse into that space. And if you have higher occluded volume, it increases the viscosity because it essentially pushes the system closer and closer to percolation without increasing the volume fraction, essentially. So that will cause the viscosity to skyrocket much sooner than normal. And so we want to capture this kind of effect when we have our viscosity model. So we want to use this true volume fraction, which accounts for the occluded volume when you consider the packing in a cluster. And this idea was featured in this paper by Don Baker from 2021, so very recently. So how do we calculate this true volume fraction? Essentially, we will, in MD simulation, we will calculate this phi star for each cluster. We'll get the packing fraction, or the apparent volume fraction, just by getting the volume of all beads and divide that by the volume of the simulation box. And then finally, we will get this phi s, which represents the fraction of protein in the cluster. And it's essentially saying you're going to identify which proteins are in a cluster. You're going to draw a sphere of radius of gyration at the center of the cluster. And then you figure out how many beads are in that sphere, and then you'll divide by the sphere volume. So now, after kind of talking about each individual piece, it's kind of, we can put together the new viscosity model. And so we based our model off of the Mooney model, and that's because we want to capture the behavior that at some maximum packing fraction, the viscosity is going to diverge. And that's what this blue term here is in the Mooney model. And so we will improve on that by we'll replace this 2.5 phi with an A, which will be used as a fit parameter. We will still keep this K phi to account for the maximum packing. And essentially, we will now have the sum of this component for the hydrodynamic stress dissipation. And then we'll have the component for the occluded volume, which is this true volume fraction. And so we can now account for these two phenomena that I talked about earlier. So how does this viscosity model perform? Well, it actually does quite well. So essentially, if a point on this chart falls on the dotted line, it agrees perfectly with experiment. And so we've taken about a dozen MABs from a lot of different solution conditions and different pHs, salinities. And we found that it performs very well overall when we couple the molecular dynamics to get this fitting parameter and this clustering information. So it performs very well. So kind of returning back to Vito, with this new viscosity model, we now can kind of put together the whole picture, where our new viscosity model is very accurate when calculating the viscosity of this IgG1. And so now we finally answer the question that this IgG1 is more viscous than IgG4, not only because of the protein-protein interactions, specifically the attractions being stronger, but the packing is more inefficient than the IgG4 in solution. So these clusters have higher occluded volume. And so ultimately, this shows that for certain cases, you actually do need to look at the structuring of the MAD clusters in solution to get a more complete understanding of how the viscosity will be affected. So to conclude, we show that these X-ray scattering SAXS experiments and molecular dynamics simulation combined, they offer a novel characterization of protein-protein interactions at high concentration. We showed that the combination of the bead-specific attraction, cluster size information are essential for understanding the complete picture of viscosity. And we also have an improved model that has better correlation to viscosity at high concentration when compared to more conventional techniques such as light scattering. And we essentially showed that our molecular dynamics simulation can be made very accurate by using these bead-specific charges, and they can capture hydrophobicity and charge all in one parameter K. And we showed that you can use this concept also to modulate subclass effects. And finally, the SAXS and simulations provide fractal dimensions and true volume fractions that are essential for viscosity modeling because we've shown that essentially you need to know the clustering information as well as the beads, the attraction and repulsion to get an accurate calculation for the viscosity. And yeah, with that, I'd like to acknowledge Amjad Chowdhury and then Dr. Naya Manohar, who did the bulk of the work for this project. And I'd also like to thank Professor Truscott and Professor Johnston, as well as Dr. Glillan and Dr. Huang for giving us form factor data to complement our SAXS experiments. And then finally, I'd like to say thanks to our sponsors, Merck and Lilly. And yeah, I'd be happy to take any questions. Thank you.
Thank you so much for such a wonderful presentation. And we do have questions rolling in, so I will go ahead and read them off one at a time. And just so everyone knows, keep those questions coming. And if we do get to a point where we can't answer any of them, we'll be sure to connect via email. So the first question we have is, what shear rate is used to determine viscosity? Do the more concentrated solutions show non-Newtonian behavior?
Yeah, so and that's something that we are working on as well. But yeah, so the shear rate, we typically do 100 to 1,000 inverse seconds, and also it's because of mainly we are limited on the material, so we typically don't have enough to do very high shear rate experiments. We've done a few, and so yeah, some of these concentrated solutions do show shear thinning when we've done the experiments. But yeah, so far we're working on trying to get more material to kind of build upon that.
And then really a follow-up and related to that is, do the models you use depend on shear rate? And I think you've kind of answered it, but to directly answer that question.
Yeah, so at least for now, they're kind of the zero shear viscosity essentially. So we've only done relatively low shear rates just due to the amount of material that we have.
And again, if anyone has questions, please just drop them in that chat panel and they will pop up on our end and we can answer them. Aside from the shear rate, someone has asked, is there a temperature dependence?
Yeah, that's also something we've been interested in as well. So unfortunately, we've only been able to do room temperature experiments so far, but we do have the capability of changing the temperature, and so we're probably going to be looking into that in the future as well.
Is there a surface tension dependence in your experiments?
Yeah, that's a good one too. So that I'm not so sure on, but I can follow up after the session, or yeah. So we still haven't we haven't looked into that either, but just we were limited by the material in this particular study.
Someone's asked, are these viscosity models also applicable to formulations of hydrophobic peptides?
That's an interesting. We've done proteins, but technically you could extend this to other molecules, and it's mainly just because we use for these models, we essentially use information that's obtained from the X-ray scattering experiments. So if you're able to set up the molecular dynamics simulation and get the SAXS measurements on peptides, yes, then this should in theory work for those as well, because yeah, we're only using SAXS and MD simulation.
Is there a viscosity limit for subcutaneous injections?
Yes, there is. I think the range is I think a little larger than like 20 or 30 centipoise is what pharma companies want to bring their concentrated solutions down to for subcutaneous. Yeah.
And are there excipients that can dissipate charge to reduce the interactions?
Yes, and that's something that we've observed too. Is that, for example, we found that arginine, we do get okay agreement, but the arginine's the cosolute that we've tried that gives the model a bit of a tough time in terms of matching experiment perfectly. And yeah, we think it's because it's somehow changing the charge distribution, or it's affecting the patches that are on the surface of the mad. Yeah, so that's very possible.
For concentrated formulation, should non-Newtonian behavior be characterized?
Yeah, I think that's a good question, and I think yes, I think it's worth characterizing it, especially with these shear thinning studies where I believe, and again, the two researchers that did a lot of the work for this project, Amjad and Neha, they did a lot more viscosity measurements than I have done, but we do think that the shear rate is, and I think also the people that we work with think that the shear thinning experiments are important because you are less stable if you start to see shear thinning the onset very quickly. So yes, I do think it's worth characterizing for stability. Yeah.
And can you elaborate on how does non-Newtonian behavior impact injectability?
Yeah, so unfortunately, I'm not too sure about that.
And someone's wondering how much sample volume is available for your testing?
Yeah, so with the SAXS, we've been able to get a lot more measurements because we only need about 30 microliters for SAXS. And typically to do a full shear thinning study, we need about 1 milliliter of material, at least just with our with our particular chip and setup. So that's why we've only kind of focused on, we haven't been able to do the full range of shear thinning studies, and we've only been able to get viscosity at relatively low shear rates because of that. So the 1 mil requirement for the full study is much more than just getting SAXS at 30 microliters.
And can you share a little about your setup, what you're using your chip setup and what it is?
Yes, actually, yeah. So the chip that we use is it's the MViroc chip that rheosense makes. We have 3 different chips. I think we have the B, C, and E chip, and we just have the syringe pump that comes with the MViroc system. So we've been using that.
Wonderful. We love that you're using the MViroc. With about 200 microliters, we can do full viscosity characterizations with our initium. So small sample characterizations on that.
Yeah, so it's I think it's just our lab SOP just might be a little different, but yeah, we've been looking into also trying to minimize the sample volume needed. So unfortunately, though, I'm more kind of focused on the X-ray studies. I've done the viscosity too, of course, but I'm a bit more familiar with the X-ray studies.
Well, I'll give everyone just another minute or two to get in any additional questions. And if there aren't any additional questions, we have had attendees say what a wonderful talk this was, an amazing presentation, and I completely agree. Thank you so much, William, for taking the time to share your research with us and to answer these questions. We have actually had one more question come in before we wrap up. Is high shear impact a consideration for structure stability?
I'm not entirely sure what the high shear impact is, if you don't mind elaborating.
I will let the person who asked that question see if they can elaborate a little more in the chat so we can get that question answered for you.
I guess, yeah, while kind of waiting for the response, we do see that like if you go to really high shear rates, the protein, for example, will denature, and yeah, so the actual stability of the proteins themselves, the conformational stability will be affected if you go to very, very high shear rates. Yeah.
I think that's what they were getting at. They just said, does shearing impact structure? So.
Oh, okay, I see. Okay, my apologies. But yeah, we tend to stay away from very, very high shear rates because, yeah, the proteins will denature and deform from that.
Wonderful. Well, again, William, thank you so much for taking the time to share all of this with us. It's been so educational and was a really great presentation.
Well, of course, thank you very much for letting me present. I appreciate it.